Please welcome Tomomasa Haraguchi, Japan Science and Technology Agency.
Hi, everyone. My name is Haraguchi from Japan Science Technology Agency, JST, which is a governmental organization in Japan. Today, we'd like to introduce you a groundbreaking company which is making innovations and waves in the world of quantum computing. That is QunaSys. JST has directly invested and supported from the beginning, so we believe they are now making innovation and breaking the walls of quantum computing. What I just wanted to tell you about QunaSys in this section is what sets QunaSys apart is unwavering commitment to innovation. Their team of brilliant scientists and engineers are now trying to unlock the potential of quantum computing and change the way we approach problem solving. Please keep an eye on QunaSys. Thank you.
Breaking the wall to material discovery through quantum computing. Tennin Yan, QunaSys.
So we all agree the carbon neutral is our humanity next milestone, but the path towards that is not straightforward. Let me give an example. Generation of ammonia, to make the fertilizer to support our food production, it consumes up to 2% of the world energy for this. And this process has been unchanged for more than 100 years. But kind of the good news is, like in the nature, if we see in the bean, there's some protein that do the generation of ammonia or nitrogen fixation far efficient than this industrial process. So kind of we can say like, okay, let's have this enzyme and use that, and we can do mass production of ammonia. But the case is like we don't understand what this enzyme reacts right now. So kind of the humanity has not that level of science to understand the nature precisely. But kind of the designing of the new materials is what QunaSys is tackling. But if you imagine designing of the new materials, what will you imagine? I think it will be something like this. Do a lot of experiment. But to be honest, this takes so much time. Typical time for from R&D start to the new materials to the market, it takes 3 to 10 years. And the materials sector is really difficult to do computational science. So kind of what QunaSys is doing as a challenge is like we use quantum computer and kind of we use that power to do the material calculations. So currently there's high performance computers, like almost supercomputers, that it's up to 40% of its time it is used to material designs. And kind of one reason we make the next generation supercomputer is to understanding of the molecules. But still, just using these classical devices, we cannot understand like a huge area of the materials study. So kind of in QunaSys, we are using developing algorithms for the quantum computer to tackle and make the next generation's materials. So let me give examples. So for the new generation of the batteries, so what we are doing is collaboration with the Panasonic. And kind of there's algorithms of quantum computer to get the energy of some really simple molecules. But what we did is like expanding that algorithms to calculate of the band structure, which is important to understand the periodic materials and to calculate that. And apart from that, what we've done with NLs is targeting the hydrogen carrier, and kind of for hydrogen carrier materials, we do molecular vibration reactions analysis and do make the kind of quantum algorithms for that. And apart from that, like towards solar energies or like the AMOLED displays, we worked with Mitsubishi Chemical to analyze the photochemical branching point analysis. But kind of just developing useful quantum computing algorithms, we think that is not enough. How can we make that industrial ready for this is also our challenges. So kind of towards that, what we are thinking is the education and developing ecosystem is also important. So kind of what QunaSys is doing is like making industrial community for education, and kind of we work with them together for the use case discovery. And also, we are making a learning platform for chemists to generate the next talent. And for that, I cannot do that alone. So kind of we are supported by strong teams. And also, we founded this company with advisors from the Osaka universities. And to make the quantum computer useful, we are just developing algorithms. So we are collaborating with hardwares like the AWS, the Google, IBMs, and other startups, and utilizing the hardware. And also we are supported by investors, and also includes hardware vendors like Fujitsu and IBM. Thank you.
I like your sweatshirt, by the way. It's written quantum native. I love that. That's the pitch. OK, we start with Frank and then Simon, please. The microphone is coming. The microphone is running. Thank you.
Thank you. Which one of the examples you showed us, of the problems you showed us, you can solve only by using a quantum computer and not by doing a simulation on a conventional machine?
Okay, so currently the quantum computer is not that powerful enough to solve something classical cannot. But we believe in 5 years from now that we are able to, like the photochemical reactions or like catalyst analysis, that area we can use quantum computer to solve something that classical cannot solve.
Okay, we have Simon. The next question, please.
Are your algorithms like agnostic to what hardware you run them on?
Yes, so kind of we are designing the quantum gates, and kind of what we are targeting is called gate-based quantum computer. So kind of we have a transpiler internally and kind of can run in all the hardware. So kind of we are hardware agnostic.
Okay. Yes, I see a question here. Are you jury also? Okay, so I need to take this priority first, but I see you. Thank you.
Thank you very much. Could you explain a bit on your business model? How do you want to earn money?
Yeah, that's good questions. So kind of currently what we are doing is like joint research, like the customer want to simulate their molecules. So kind of we will help them and developing algorithms for that companies. But in the future, what we are currently pushing is like working with hardware companies. So kind of on their platforms, they implement our software. So kind of the software, we make software and hardware integration, and user just call the API from outside. So that is kind of what we are trying to do.
So I see no one. I see Elizabeth and the jury, and it's going to be difficult. I'm sorry. First, Elizabeth.
I wanted to modify Frank's question in terms of your algorithms. So how do you measure the superiority of solving the problems with your algorithms in comparison to existing modeling approaches?
So kind of, thank you, that is a really good question. So currently a quantum computer, what we can do is like we call like 50 qubit size. But kind of when the powerful quantum computer will be powerful, it's like the 1,000 qubit of size. So kind of we are more like extrapolate what the algorithms we have in that size, and also benchmark the classical result and see where's the crossing point. So that's kind of how we benchmark the powerfulness of our algorithms.
Thank you. you. So I'm going to take your question. This is what you see. People who are not jury, you still have a chance sometimes. Go on.
Thank you very much. So I'm curious about the accuracy. So for all of the projects you have already calculated, are there any experimental data also supports afterwards to prove your calculation result? And if you did that, how much the accuracy rate you can meet?
Yeah, so kind of what we are doing is like solving the Schrödinger equation, and kind of for that in the we are kind of the accuracy is like the kind of the theoretical limit of that. But still, even we calculate theoretical limit, there's like in the real life there's a thermodynamics that affect, and kind of that will vary. So kind of we are calculating at the theoretical limit, but how to integrate with the real experimental data, that is our challenges, and we think there's a lot of machine learning method for that. So kind of we are trying to collaborate with that kind of algorithms and techniques.
Wonderful. We have 5 seconds left, so all the rest will have to wait for the lunch break. Thank you very much.